discusses the features and advantages of ARM processor in embedded applications. All information is from ARM System Developers Guide by Sloss, Symes and Wright. In this video, the focus will be on the hardware features and how ARM processor, the bus, memory, and peripherals interact with each other in an embedded application. Starting with the ARM processor, it is the controller of the embedded device, and it is the main execution engine that processes the data and interacts with other components by executing the instructions. A bus is a communication channel between the processor and all other parts of the device. In x86 architecture, it is the PCI peripheral component interconnect bus that is connecting the other devices to the x86 processor. It is an external or off-chip and built on the motherboard, and it has to be connected mechanically and electrically. As compared to that, embedded devices use the on-chip bus. The on-chip bus is internal to the chip and it is used to connect with the peripherals. There are two classes of devices attached to the bus. One class of device is the bus master, which is usually the ARM processor, and it can initiate a data transfer with another device. A bus slave or a peripheral is a device capable of responding to the request from the bus master. For whatever transfer request, it will respond. Continuing with the bus, there are two architectural levels. One is at the physical level, which is governed by the electrical characteristics of the bus and the width of the bus in terms of number of bits like 16, 32, etc. At the second architecture level, which is at the level of protocol, it is a logical rule set of rules that is used to communicate between processor and a peripheral. AMBA, Advanced Microcontroller Bus Architecture, which was announced in 1996, is most commonly used. It has two parts, ASB, which is the ARM system bus, and the APB, which is the ARM peripheral bus. Large number of peripherals have been developed by it, and hence the peripheral designers can readily reuse these peripherals. The hardware designers have a wide choice of the peripherals as they are tested and already proven, and these can be simply bolt onto the chip bus without any redesign that is needed. Because of such plug and play, the uh, the time to market is highly improved. There are new enhancements to the bus protocol in terms of AHB, which is the ARM high performance bus. It provides higher data throughput than the traditional ASB. This is due to the centralized multiplexed bus scheme versus the bidirectional bus design. It allows to run at the higher clock speeds, supports higher widths in terms of 64 to 128 bits, and there is a single active master at any time. However, in multiple variants of the AHB bus, in one variant called multi-layer AHB, it can allow multiple active bus masters at the same time. It has a different interconnect, but it is usually used for systems with multiple processors. As operations occur in parallel, the throughput rates are high. Another variant of AHB bus is the AHB Lite, which is which has a limitation of a single bus master, and it is used for embedded devices and designs that do not need all the features of AHB bus. The protocols that are used for master and slave are the same. Moving on, the next is memory, which is characterized in terms of hierarchy, width, or type. Focusing on the hierarchy of the memory, the processor cache is the highest cost and the most efficient with fast speed for data transfer as it is physically located near the processor. The secondary memory, which is set farther away, is relatively of lower cost, but the capacity is higher. Usually this is stored in a separate chip, which is different than the processor chip. Load and store architecture and instructions are used to access from the secondary memory. In addition, there is the more economical, slower speed, but largest capacity secondary storage that can be used for data storage. Considering the memory width, it is the number of bits returned when the memory is accessed in one operation. This comes in variants of 8 bits, 16 bits, 32 or 64 bits. The number of bits has a direct effect on the overall performance. For example, while 32-bit ARM instructions interoperating with a 16-bit wide memory chips, the processor has to make two memory fetches per instruction because a single fetch can return only 16 bits from a 16-bit memory width. This leads to reduced system performance. However, it is less expensive because the number of bits are less. The ARM architecture supports thumb instructions, which are 16 bits. This gives a better performance with a 16-bit memory as only a single fetch is needed to load an instruction. With reduced cost, the 16-bit thumb instructions ARM processor and 16-bit memory enable embedded systems which are economical. The another aspect of memory is the type. Read-only memory is is the is the least flexible, non-programmable, and permanent memory which is used by the embedded system for operations like the boot code. This type of operations do not require any updates or corrections. The next is the flash ROM, which can be read and written to. The writes are slow and it is usually used for device firmware. This can be used to store data when power is turned off. It is software controlled and erasing and or writing do not need any additional hardware circuits. This leads to reduced manufacturing costs and is an alternative to secondary storage. Dynamic random access memory, also called as DRAM, is most commonly used because it has the lowest cost per megabyte. However, it is dynamic in a sense that the storage cells have to be refreshed by giving electronic charge every few milliseconds. Hence, before setting a DRAM controller, before setting up the DRAM memory, it is needed that the DRAM controller should be started. DRAM is asynchronous, so does not burst as efficiently. Burst means the amount of data that can be given out of the memory. Synchronous DRAM is another subcategory of DRAM memory. It runs at a higher clock speeds and it synchronizes with the processor as it is clocked. It has a better burst because the data fetched from memory cells is pipelined and brought out onto the bus in a single burst. SRAM or static random access memory is faster because access time is considered shorter because there is no pause needed between data accesses. It is static. There is no need of continuous electrical signals for refresh. However, it requires more silicon area and higher cost. It is used mostly for high-speed tasks. Peripherals are external to the chip and they perform specialized functions like input and output by connecting to other devices and sensors. Peripheral performs a specialized single function and it may also reside on chip. Another complex example of a communication device could be a wireless peripheral device. The communication is memory mapped and programming addresses are set as memory addressed registers. Address of these registers is an offset from peripheral base address. The peripheral devices determine the uniqueness of the embedded devices based on its organization with ARM processor. Example of peripherals are controllers, which implement some higher level functionality, and the two most commonly found controllers are memory controller and interrupt controller. Looking at the memory controller, it is a connect. It is used to connect different types of memory to the processor bus. On powering up a controller, the memory controller is configured in hardware and it allows memory devices to be active. For example, the initialization code can be executed from the memory. Some memory devices have to be set up by the software as we saw in the dynamic RAM. Another type of peripheral is the interrupt controller. An interrupt controller provides a programmable governing policy. What it means is that there is a software that can determine what interrupts can be allowed at any specific time. These these interrupts can be programmed by setting appropriate bits in the interrupt control registers. For the ARM processor, there are two types of interrupt controllers. A standard interrupt controller sends an interrupt signal when the external device requests servicing. The, this particular interrupt signal can be ignored or masked based on the programmed for the individual device. It reads the device bitmap register and determines what device has raised the interrupt and requires servicing. Another type of interrupt controller supported by ARM is the vector interrupt controller. It is more powerful than the standard interrupt controller as it can prioritize the interrupts. It can also simplify the determination of the device that raised an interrupt by associating a handler address. It can assert if an interrupt has sufficient priority so that any current interrupt handler can be paused and another could be serviced. In case interrupt is to be serviced, VIC has two options by in the first case by calling the standard interrupt execution handler and this can load the address of the handler from the device from the VIC. The another option is to directly cause the ARM processor core to jump to the handler for the device.